Welcome to this discussion on probability. The word probability and its variations have slowly crept into our daily life and vocabulary. We hear them in weather forecasts, sports predictions, and election analysis. Now, what is probability? The probability of an event is a numerical measure of the likelihood of occurrence of that event. Usually, the concept of probability is associated with random processes whose outcomes are not entirely predictable. The concept and theory of probability finds widespread applications in astronomy, biology, economics, healthcare, and sociology. It is used extensively in lottery and casino game designs, in determining appropriate insurance premiums, in making corporate investment decisions, etc. There are complex probability models and probability distributions that find application in practical real-life situations. However, they are beyond the scope of our discussion here. The focus here is to improve your ability in solving probability-based questions that are part of aptitude tests, and we shall restrict our discussion to such situations. Let us start with a simple and frequently used example, that of tossing a coin. What is the probability of getting a head when you toss a coin? I'm sure you would have got the answer as 1/2. But how did you get that answer? Let us analyze the situation. When we toss a coin, there are only two possible outcomes. You could get a head or you could get a tail. Further, only one of them will occur at a time. If we assume the coin to be an unbiased coin, then these two outcomes are equally likely. Therefore, the probability of getting a head will be 1 out of 2 or 1/2 or 0.5. In this case, the probability of occurrence of the event was found using a theoretical approach. This probability is sometimes called classical probability. As per the theoretical or classical definition, probability of an event P of E is equal to the ratio of number of favorable outcomes to the total number of all possible outcomes of the experiment. It should be noted that in this classical definition of probability, all the outcomes of the experiment should be equally likely and mutually exclusive. This is something that should not be overlooked. The classical definition will not work when the outcomes under consideration are not equally likely or are not mutually exclusive. At this point, I think it will be unfair on my part if I don't explicitly describe some of the terms and terminologies used here. Experiment. An activity like tossing a coin or a die whose result is random in nature is what we call an experiment in probability-related discussions. It can be simple ones like tossing a die once, or it can be a little more complex like tossing a coin 5 times or tossing 3 dice simultaneously. An iteration or repetition of the experiment is called a trial. Results of a trial of the experiment are called outcomes. In the coin tossing experiment, there are 2 outcomes, head and tail. In the case of tossing of a die, there are 6 outcomes, 1, 2, 3, 4, 5, and 6. The set of all possible outcomes of an experiment is called the sample space of that experiment. Sample space is usually denoted by S. In the coin tossing experiment, sample space S will be head and tail. In the die tossing experiment, sample space S will be 1, 2, 3, 4, 5 and 6. Each possible outcome of the experiment is called a sample point. It will be an element of the sample space. Any subset of the sample space is called an event. Stated differently, an event is a collection of one or more outcomes of an experiment. The aggregation could be based on some specified criteria. An event could be as simple as getting a 2 when a die is tossed, or it could be something like getting exactly one king and one queen when 2 cards are picked from a deck of cards. An event could also be a function or derivative of the outcomes. For example, sum of die values being a prime number when 2 dice are tossed. The maximum value of probability is 1 and the minimum value is 0. Probability of a sure event is 1 and that of an event that will never occur is 0. All other probability values will be between 0 and 1. A sizable number of questions on probability come from experiments involving coins, dice and deck of cards. Let us start with a dice-based question. Refer the question number 1 given in the slide. 2 dice are tossed simultaneously. What is the probability that the sum of the die values is 6? When you toss a die, there are 6 possible outcomes. 1, 2, 3, 4, 5 and 6. Thus, when you toss 2 dice, there are 6 into 6 or 36 equally likely outcomes that can occur. They are shown in the slide. The first value within the bracket gives the value on the first die and the second value in the bracket gives the value on the second die. All these 36 outcomes are equally likely. That is, there is no preference for any of these outcomes over the others. All these 36 outcomes are mutually exclusive as well. That is, 2 of these outcomes cannot occur together. The outcomes that will give a sum of 6 can be seen along the red band. Thus, the outcomes that are favorable to the event of getting the sum of 6 are 1 and 5, 2 and 4, 3 and 3, 4 and 2, and 5 and 1. Out of the total 36 outcomes, there are 5 outcomes that are favorable to the event under consideration. So, the probability of getting a sum equal to 6 equals number of favorable outcomes divided by the total number of equally likely mutually exclusive outcomes, which equals to 5 divided by 36 or 0.138. Let us now solve a similar problem. See the question number 2 given in the slide. When 2 dice are tossed simultaneously, what is the probability that the sum of die values is a prime number? As in the previous question, here also there will be a total of 36 possible outcomes. All these outcomes are equally likely. That is, each one of them has the same chance of occurrence. They are mutually exclusive as well. That is, only one of these 36 possibilities will happen at a time. The sum of die values could be anything between 2 and 12. Of these, the prime numbers are 2, 3, 5, 7 and 11. All these are favorable for our event of sum being a prime number. The sum of die values will be 2 when the outcome on the dice is 1 and 1. That is, there is only one possible outcome which will give the sum as 2. The sum of die values can be 3 in two different ways. It could happen with 1 in die 1 and 2 in die 2, or with 2 in die 1 and 1 in die 2. Similarly, as shown in the figure, the sum can be 5 in 4 different ways. The sum can be the prime number 7 in the case of 5 different outcomes, and the sum of die values can be 11 in 2 different ways. Altogether, we can see that there will be 1 plus 2 plus 4 plus 5 plus 2 equal to 14 outcomes which are favorable to the event under consideration. Thus, the probability of occurrence of the event, sum of the two die values as a prime number, will be number of favorable outcomes divided by the total number of equally likely mutually exclusive outcomes, which is equal to 14 divided by 36, which is 0.39. Let us now consider a probability question based on tossing of a coin. Read question 3 given in the presentation. A coin is tossed thrice. What is the probability of getting a head at least once? Let us analyze what happens when the coin is tossed thrice. When we toss the coin for the first time, there are two possible outcomes. It could be a head or a tail. What about the second toss? There also, it could be a head or tail. Will the outcome of the second toss depend on that of the first? No. The second toss is completely independent of the first toss, and the result of the second toss could also be either a head or a tail. Similarly, the third toss of the coin also can give us either a head or a tail. It does not depend on the result of the earlier tosses. The exhaustive list of all the possible outcomes of the experiment or the sample space is given in the slide. There are 8 possibilities as shown. How many of these outcomes would be favorable for our event under consideration? What we want is to get a head at least once during the 3 tosses of the coin. Note that we are looking for at least one head. That is, minimum one head. It can be more than one, no problem. That means we can count outcomes in which heads occur twice and thrice also. We can see that there are 7 out of 8 outcomes which have at least one head. So, the probability that we will get at least one head when we toss a coin thrice equals number of favorable outcomes divided by total outcomes, which in this case is 7 divided by 8 or 0.875. When you analyze a problem or a question, you should try to solve it using different approaches. This will enhance your understanding of the fundamentals and give new ideas to tackle different situations. Question 3 can be solved using a different approach by making use of the complement rule in probability. It is easy to understand. Take any event. The probability that the event happens plus probability that the event does not happen will be equal to 1. This is because it is sure that the event will either happen or it will not. Probability that the event does not happen is same as probability that the complement of the event happens. Therefore, P of E plus P of E complement will be equal to 1. Therefore, P of E equals 1 minus P of E complement. In this question, we had to find out the probability of getting a head at least once during the 3 tosses of a coin. What would be the complement of this event? That is, when would the event under consideration not happen? The event will not happen when none of the 3 tosses give a head. For this, all the tosses should give a tail. So, the probability we are looking for can also be found as 1 minus probability that the complement of the event happens. That is, 1 minus probability of getting all 3 outcomes as tails. Probability of getting tails in all the 3 tosses is 1 out of 8, as can be seen from the slide. So, the probability of getting at least one head when the coin is tossed thrice will be 1 minus 1 by 8, which is equal to 1 minus 0.125 equals 0.875. Another favorite area of probability question setters is the deck of cards. Let us look at a simple question based on playing cards. Refer the question 4. It asks you to find the probability that all 4 cards picked from a deck of 52 cards are spades. Let us understand what constitutes a deck of cards before we move forward. A complete set of cards is called a pack or a deck. The standard deck of playing cards contains 52 cards. A subset of cards held at any one time by a player is commonly called a hand. The 52 cards present in a deck are divided into 4 suits, namely spades, hearts, diamonds, and clubs. Thus, there would be 13 cards in each of the 4 suits. Further, the suits are color-coded. Diamonds and hearts are red, while clubs and spades are black in color. Sometimes, the deck of cards may include special cards that do not belong to any suit and are often called jokers. However, if nothing is said explicitly about their presence, we usually assume that they are not there and that the deck contains 4 into 13 or 52 cards. The 13 cards within a suit are ranked or marked 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, Queen, and Ace. Thus, for each rank, we shall have 4 cards, 1 of clubs, 1 of diamond, 1 of hearts, and 1 of spade. For example, we would have 4 aces, a club ace, a diamond ace, a hearts ace, and a spade ace. In question 4, we are picking 4 cards at random. In a deck, there are 52 cards and all these 52 can be identified separately. So, the total number of ways in which we can pick 4 cards from these 52 will be 52C4, whose value is 52 into 51 into 50 into 49 divided by 1 into 2 into 3 into 4. This is the total number of outcomes of the experiment. If you are not clear on what is meant by 52C4, I advise you to refer the discussion on combinations. The 52C4 ways in which we can pick 4 cards from the deck will have the following possible scenarios. We will have picks in which all 4 cards are spades. We will have picks in which none of the 4 cards are spades, and picks in which some of the 4 cards are spades. We know the total number of outcomes is 52C4. What will be the number of favorable outcomes? How many different picks will be there in which all 4 of them are spades? If we want to ensure that all the 4 cards picked are spades, then we should pick the cards from the set of spades. We know that there are 13 spades in a deck of cards, and so we will have 13C4 different ways of picking 4 spades from a deck of cards. So, the number of favorable outcomes in this case will be 13C4. So, the probability that we are looking for will be number of favorable outcomes divided by total number of outcomes, which in this case will be 13C4 divided by 52C4, whose value is 0.0026. Let us solve one more question before we end this discussion. In this question, we have a class of 50 students, of which 30 are girls and 20 are boys. The teacher selects 2 students from this group at random. What we want is to find the probability of these 2 students being both girls or both boys. Let us first look at the total number of outcomes possible when the teacher picks 2 students at random. There are a total of 50 students, all of whom are different. The total number of ways in which 2 students can be picked from this set of 50 students will be 50C2, the value of which is 50 into 49 divided by 1 into 2, which is 1225. Among these 1225 different possibilities, we will have selections in which both the students are boys, selections in which both the students are girls, and selections in which it is one boy and one girl. In this question, we are to find the probability that the chosen students are either both girls or both boys. Let us now find out the number of favorable outcomes among the 1225 possibilities. There are 30 girls among the 50 students. So, the number of ways in which we can choose 2 girls is 30C2, which will be 30 into 29 divided by 1 into 2 equals 435. There are 20 boys among the 50 students. So, the number of ways in which we can choose 2 boys is 20C2, which will be 20 into 19 divided by 1 into 2 equals 190. So, the number of ways in which the teacher can choose either 2 girls or 2 boys will be equal to 435 plus 190, that gives 625. Note that we applied the addition principle of counting here. Now, the required probability can be found out as the ratio of favorable outcomes to the total outcomes, which is 625 divided by 1225, that gives 0.51. In all the questions we discussed here, we expressed likelihood as a number between 0 and 1. There are also a couple of other ways in which the chance of occurrence of an unpredictable event could be expressed. Let us consider the case of tossing of a coin. Consider the event of getting a perfect square as the outcome. There are 2 favorable outcomes, 1 and 4, out of 6 total outcomes. So, the probability of getting a perfect square when you toss a coin will be 2 divided by 6, or 0.33. Another way of expressing this chance is in terms of percentage. This is obtained by multiplying the probability value with 100. Thus, we can say that there is 33% chance of getting a perfect square when we toss a coin. When we express chance of occurrence of something in terms of percentage, the value should be between 0 and 100. Thus, a probability of 0.5 corresponds to 50% chance. A probability of 1 corresponds to 100% chance. There is another, not so common way of expressing probability in terms of odds. This expression is the ratio of number of favorable outcomes to the number of unfavorable outcomes. Alternatively, it could also be taken as the ratio of probability that the event happens to the probability that the event does not happen. In the case of our present event, the odds of getting a perfect square on the throw of a dice will be number of favorable outcomes is to number of unfavorable outcomes, which is equal to 2:4 or 1:2. Through this presentation, you would have got a clear idea about the basic concept of probability. We have restricted this discussion to simple situations. If you feel comfortable with these concepts, you are ready to move further up the learning curve. In the other discussion on probability, we have discussed more complex concepts like dependent events, joint probability, and conditional probability. Thank you.